Now that we've learned about formatting and balancing chemical equations or chemical reactions, I'd like to talk through some of our typical ones. So common categories of chemical reactions that you tend to see again and again in chemistry. I'm just going to walk through these and talk through some of the common elements of reactions of that type that help indicate that it is that type of reaction. So first I'll start with combustion reactions. Combustion reactions are when you have oxygen gas as a reactant. And so here we have our oxygen gas, there's 5 of them, reacting with propane, which is C3H8. So this is the propane combustion reaction that takes place in my barbecue. So the thing that's interesting about combustion reactions is they take a fuel source and oxygen, and with an ignition, they'll burn, and they produce a lot of heat. It's we call it exothermic reaction, which just means it produces a lot of heat, often light, and we take advantage of this reaction all the time to move vehicles and to cook food, right? Or just warm ourselves as well. And typically, the fuel source is what we call a hydrocarbon, something that has carbon and hydrogen. Sometimes it'll have other things too, or sometimes there isn't carbon involved at all. Like we saw an example already of hydrogen combustion, which just forms water. If carbon is involved as one of the reactants, then your products will always include carbon dioxide. So what's happening here is, let me get a different color. The carbons of the propane of your reactant here are now the carbons of the carbon dioxide. And the hydrogens of your reactant, of your propane that you started with, are now water. And they are splitting up all the bonds of that propane molecule and combining the carbon and hydrogens with oxygen instead. So you get carbon dioxide and water as a product. And so when you're looking at a reaction, you're like, is this combustion? You'll usually see an oxygen on, or you will always see an oxygen on the reactant side, and then carbon dioxide and water if you are looking at a reactant that has carbon and hydrogen. There are other, if you have like limited oxygen around, then you might see other products as well. You might see carbon monoxide, or you might see just carbon on its own as a solid. Those tend to happen when we have less oxygen available to form carbon dioxide. So not as stable. All right, so those are combustion reactions. These are ones that we focus on a lot in our cannabis class because we were talking about phase transitions into the gas phase for a lot of our compounds, like our cannabinoids and our terpenes, and trying to get those into the gas phase without combusting them. And our fear around combustion of our terpenes or our cannabinoids was that we would be breaking apart all of those bonds that create the structure of the molecule and simplifying them into just carbon dioxide and water, which would not have the same medicinal benefits at all as something like THC. Another common reaction is an acid and base reaction. These reactions are when we have a reactant that we identify as an acid and a reactant we identify as a base that are mixed together. And they typically form a salt and water. And this reaction is actually called the neutralization reaction that I'm showing here. Acids, so here is our acid, it's HCl, and our base is this sodium hydroxide. You don't need to memorize what common acids are or bases. But when we bring an acid and a base together, they are going to neutralize each other. And the neutralization is really talking about the pH. So really high pH or low pHs can harm you. Like your body's at a pH of 7.4. pH is really just a measure of the number of H plus ions, so protons, or H3O plus, which is that proton bonded to a water that are in a solution. And if you have too much of those, or if you have too many hydroxides, so these are different ions, then you will, like your body, if you have too many of those, then you're in a situation where more chemical reactions will take place with those acids and bases, which can be damaging to tissues. So when we bring them together, we are neutralizing their pH into something that is safe, typically. So here we're showing hydrochloric acid and sodium hydroxide form sodium chloride and water. So we have something that is a low pH, which is an acid, and a high pH, mixing to form a neutral pH, which would be around 7. So to identify an acid-base reaction, you're really looking for a salt and water as a product. And we could spend weeks talking about what is an acid, what is a base, why do they react together, how do we know they have, and doing all sorts of fun calculations. But we're just going to focus on identifying reactions that are acid-base reactions, be like, oh. And so I would say overall, what's really happening in these ones, in its simplest form, is that protons, so hydrogen atoms that have lost their electron, are being exchanged between different molecules. So these bonds to a hydrogen are breaking, and then that hydrogen is forming a new bond to a different chemical. And so the changes between them can be between reactants and products can look pretty subtle because it can be just the difference of one hydrogen. And let's look at decomposition reactions next. Decomposition reactions are when we have something that is a chemical, so it's a single thing as a reactant. So my big tip is always that there's a single reactant. So here we just have water as our reactant. That's it. And it breaks down into multiple products. And what it's doing is it's separating the elements that made up our reactant. And so we can see we have our hydrogen is now part of H2, and our oxygen is part of O2. And so we're separating. The decomposition reaction takes a chemical formula with multiple elements and separates them into their individual elements. Sometimes it does this by combining it with something else, but it's basically a separation reaction. We call it decomposition. And this will take on a lot of different forms. Sometimes we'll see it. It'll be really clear like this one where our water is decomposing into hydrogen gas and oxygen gas. Sometimes you'll have your elements separated, as I said, with something else on one of them. But these are usually happening over a period of time too. They're usually triggered by exposure to light for a lot of reactants. When we talk about how THC can decompose over time, we're really looking at longer periods of time and light exposure or heat exposure that make the reaction take place. And so to prevent decomposition reactions, we typically see the type of glass the chemical is stored in change from clear to a dark brown or green to limit the amount of light that gets through the glass bottle to the reactant, or storing it in a dark locker or cabinet is also effective. And making sure it's in a temperature controlled environment. Sometimes putting it literally in the fridge, kind of like we would put food that we don't want to have spoil, helps a lot. All right, next we have single and double replacement reactions. So in these ones, we either have one ion switch which cation it is bonded to, or two. And I think these types of reactions are most famous for precipitation reactions that are kind of in this category. So I put my favorite one here, where you bring together potassium iodide and lead nitrate, which are both clear solutions. And when you mix them together, suddenly a bright yellow solid appears. And that's the lead iodide right here. So this lead iodide is the solid that you're seeing in the test tube. And it looks like magic when it forms, which is why I think they're such fun reactions. But what's happening here is our lead, which is originally ionically bonded to these nitrates, but dissolved in water, so separate. When it comes into contact with an iodine, it forms a solid rather than an aqueous solution. And aqueous just means dissolved, right? So it's basically saying, oh, if lead is in the presence of iodine ions, it won't be able to dissolve in water. And so it'll form this solid, this brightly colored solid very quickly. Now, our potassium and our nitrate are soluble in water, and so there's still just a clear solution. And we don't see any like observable change at all. But what's basically happening here too, right? No, I'll do this like this. Is we're swapping the cation and anion of our two compounds. We're combining. So you could just take the cation of one and the anion of the other and ask yourself, oh, is this going to be insoluble or not? And then the anion and the cation that remain, and are these soluble or not? We have these solubility tables, so you can look it up and say, like, oh, look, all lead compounds except for these few would be soluble in water or insoluble in water. And so there are these are available. You can find them online easily. They're in reference books for chemistry as well. And they're guidelines to kind of sort out which compounds tend to have high or low solubility in water. Right, the last kind of common reaction that I want to talk about are reduction and oxidation reactions. We oftentimes just abbreviate these redox for reduction and oxidation. And these ones are really about electrons moving between reactants to form some new products. Some of these are easier to see than others. And I love this example because it has a color change, and also it's easier to see things change from the element to something that's an ionic compound. So in this reaction, we have copper chloride, which is a salt, right? So that really means that our copper is a copper +2 ion, and it's soluble in water. That's giving us this blue solution right here. So this is copper ions dissolved in water will create a blue color. And then we have zinc metal, which has a charge of 0 because it's just an element. That is right here. Here's our zinc. And so we just have a strip of zinc metal. When these are brought together, a spontaneous reaction occurs where electrons flow from the zinc to the copper. This is actually the foundation of battery chemistry, right? So this flow of electrons can create an electrical current. And what happens is as the zinc gives up electrons to the copper becomes a element without a charge. And our zinc, which is losing our electrons, becomes zinc +2. And so in our product, what we see forming is copper solid. And that's that black part. So that's just solid copper forming on that zinc strip. And you'll notice that our solution is getting clearer and clearer. It's less blue. And that's because we now have zinc +2 ions dissolved in it and less of the copper +2 that give it that blue color. And so we can see this solid form. We see the color of the solution change. And all of this is because an electron is going from our zinc to our copper, which I think it's a really cool type of chemistry. We see this in less obvious reactions too. Actually, combustion reactions are also redox reactions. We don't have charged ions floating around, so it's much harder to see. But our oxygen goes from an elemental state with a charge of 0 into a state where it's bonded with carbon and with hydrogen. And it actually requires a little flow of electrons between the carbon and the oxygen to form that, which is super interesting. And so redox reactions don't have a specific format to them that'll make them easy to identify. Sometimes you'll see a charge change, and that will give you a clue that you're looking at a redox reaction. But they are also one of the most common ones that we have.